Ladies and gentlemen, I would like to welcome you to another exciting session of my private research project that is about the SensGuitar. I am particularly pleased to be able to talk about this work today, as my presentations on this endeavor have never been so compact as so close to the end of this research project. I have never been able to talk about so many artifacts at once as I have today, and questions will probably never be so versatile. I have prepared the following outline for the presentation sessions. In the first session, I wanted to motivate and started from the state of the art. We have addressed how traditional guitar building and modern computer systems can be brought together. Why was it necessary to conduct this research? What do we get out of it? Which kinds of requirements do we have to satisfy, and how was proceeded will be addressed in today's presentation session. Here I clarify what the results of a design science-oriented research should look like. Then we come to the presentation of the product or the artifact that was created, the SensGuitar and its feedback and visualization possibilities. How this was applied in scenarios will be addressed in the next session, which is called demonstration. This is followed by the approach of evaluation using requirements specified in advance in 3 relevant examples. First, education, second, production, and third, band. The final agenda item identifies limitations and addresses the need for further research. Please remark, the topics on the SensGuitar are so huge so that I have split up this into several sessions. So let's focus on today's agenda points first. Today we are going to focus on the design of the SensGuitar. Before this, we address requirements of the construction process. Since numerous topics are brought together here, I'm going to guide you through the slides topic-wise. Finally, an interim conclusion will be drawn, so that we are ready to go for the next presentation session. I suggest we have many agenda points to conquer. Let's start right away with a recapitulation. In the last presentation, we have addressed the research motivation. Among further, we have detailed the technical perspective on guitars. These refer to non-digital systems, non-autonomous systems, non-intelligent systems, non-feedbacking systems, and non-adapting systems. For further details on these key points, please have a look on the last session. Further, we have detailed the situational perspective on guitars. These realize inefficient knowledge transfers. Only late feedback is enabled by them. This feedback is only provided by third parties. Thus, low qualitative collaboration results can be expected. If you are interested in further explanations on this, please have a look in the last session. However, the research question was the following. How can stringed musical instruments, such as guitars, be made intelligent to enhance knowledge transfer? Further, in the last session, we have conquered the generalization and abstraction of a guitar process. Our interim conclusion was that the traditional guitar is considered as passive tangible resource object only. It's indicated in blue here. At least this accounts for the 3 scenarios addressed and the standard electric guitar considered. Please get detailed information about this from the last session. Let's now come to the new stuff from today's perspective. How to consider the theoretical foundation presented for the development process. Let's address the first requirement. In accordance with Pevers et al., requirements are specified at the very beginning of a research. Prior to the design of an artifact that shall solve a certain research problem, these are collected in order to narrow down solution approaches. Further, they function as quality gate to complete research phases of first, the initial development, and second, on-building development. Later at the presentations, They will serve for the evaluation in how far requirements have been satisfied by the artifact created. So much about the methodological proceeding of this research. Let's come to the most relevant requirements collected for this research. First, enhancement. Traditional stringed musical instrument designs need to be enhanced. It's not intended to construct a completely new product. A new potential shall be realized, such as the increased feedback opportunities because of the integration of technical components. However, the traditional handling of stringed musical instruments may not be limited because musicians are used to it. Second, digitization. The mechanics of a stringed musical instrument need to be digitized so that a digital twin is created. Analog electric signals need to be transformed to digital signals so that these can be processed by computers embedded at the instrument before analogizing them again and routing them through standard output sockets. Third, IoT integration. Internet of Things integration. The stringed musical instrument as technical device need to be integrated in the IoT structure, so that a communication by the stringed musical instrument and further dialogue partners can be realized. These partners can refer to further sensitive instruments, alternative devices, and human process participants. Fourth, cyber-physical system capabilities. The stringed musical instrument needs to provide components of sensors, actuators, processors, and communicators so that cyber-physical system capabilities can be realized. Fifth, knowledge transfer improvement. As the instrument design has not a purpose in itself, the artifact needs to improve knowledge transfers. In accordance with the validated knowledge transfer models, here, for instance, task complexity or knowledge thickness need to be reduced or competence need to be raised in order to raise knowledge transfer speed. These requirements have guided the development process of the SensGuitar. But roughly speaking, what is the concept of sense instruments? Let's face the design of the SensGuitar as artifact. One of the design perspectives on the SensGuitar refers to the physical nature of the artifact. Here you can see the 3D modeling of the conceptual instrument and its components. We are going to face them component-wise. It provides one large display that serves as fretboard. This serves as actuator by visualizing content. For instance, the SensGuitar can visualize feedback about a musician's playing. So it attempts to manipulate its environment, referring to the musician for example, in order to improve guitar playing. Further, if a touch is put onto the display serves as sensor. For instance, so the SensGuitar recognizes the musician's current playing. The wooden body integrates electronic boards and computing units. These refer to the cyber-physical systems, processors, and communicators. For instance, these can process sensor data in order to generate a feedback. Any kind of information, such as fingertips, feedback, etc., can be communicated via wireless antennas. Traditional buttons and switches have been integrated with the sensitive instrument design. This means that the buttons and switches can serve as both sensors and actuators. For instance, as the SensGuitar detects the button and switch configuration, the processing can be affected, such as the current sound design. These can serve as actuators if the SensGuitar modifies the button switch configuration autonomously. Flexible jacks can optionally be considered as input and output of audio signals. Thus, they can serve as both sensors and actuators. For instance, these serve as sensors if external inputs such as microphones, MP3 file signals, or further instruments are inserted and recorded. On the basis of their input, the SensGuitar can process audio information. In the case the SensGuitar outputs an audio signal manipulation, the instrument attempts to manipulate its environment, referring here to the audio signal, in order to improve guitar sound appearance. Piezoelectric and magnetic pickups can be used as sensors. By them, different kinds of audio signals are input to the SensGuitar. To be more concrete, in this case, we speak about 6 piezo pickup signals, 1 per string, and 2 magnetic pickups signals. The controlling display serves as controlling panel. This serves as actuator by visualizing content. For instance, the SensGuitar can visualize app information about a musician's playing. So it attempts to manipulate its environment by activating the musician in order to improve guitar playing. Further, because of its touch panel that is stuck onto the display serves as controlling sensor. For instance, so it recognizes the musician's current controlling activities. As an interim conclusion, one can recognize that the cyber-physical system capabilities support the autonomous feedbacking by the SensGuitar. As we now know the concept of sense instruments, how can it be embedded in its environment so that it can realize the full technical potential? Here we speak about the architecture of an infrastructure, which refers to one further design perspective on the SensGuitar. The infrastructure needs to provide the following components by design. First, the SensGuitar, which is designed as cyber-physical system. We have clarified the individual cyber-physical system components, the presentations before. Remember, sensors, processors, actuators, communicators, etc. Further artifacts can be found here, such as scale patterns, songs or feedback patterns, which are loaded by the applications of the SensGuitar. Which kinds of these knowledge objects shall be considered in a certain situation will be controlled by the simulation and knowledge management instance. This controls simulating a certain song too. The local knowledge base provides the artifact situation relation, so that the local knowledge artifacts can be organized efficiently. Second, the sense instrument environment that integrates several sense instrument systems. You can see it here on the right. This organizes several sense instrument systems. All of them are connected via global communication server, so that you, from a technical side coming, can connect as many systems as you want. Of course, the original musician needs to control this. Who is allowed to see my musical playing? Please note further, although each further system provides its individual local knowledge base, these follow the same cyber-physical system structure than the SensGuitar shown on the left. So they have sensors, processors, communication clients, actuators. A global knowledge base will make accessible in addition, so that the instances can share their objects, their scales, their songs, their feedbacks, if desired. Third, a third party such as a teacher, producer or band member having individual sense instruments or further devices are part of the architecture. Since the devices of these parties follow the same cyber-physical system structure than the SensGuitar, shown on the left, the guitarist activities can be visualized on the remote device. So the guitar is activated by the musician here. It's communicated via the global communication server and visualized on the devices of the teacher, producer or band. Further, because these devices allow a bidirectional information exchange, activities of these parties can be sent back. So from here to the SensGuitar in order to be visualized on the musician's SensGuitar. As an interim conclusion, I want to picture out that the infrastructure embedding of the SensGuitar supports the collaborative way of making music, which is because of the bidirectional interplay of components presented. This will serve as basis for the next slides and further explanations. As we now know how the SensGuitar looks like and how it is interwoven within an infrastructure, let's now face the design of novel forms of interaction which are enabled because of the SensGuitar. The following 10 kinds of novel forms of interactions are supported by the SensGuitar. First, next notes. This novel form of interaction refers to the act of visualizing next notes on the guitar fretboard that are required by a certain song. Aside highlighting the precise fingertip position, this includes highlighting the corresponding string attack position so that a note is characterized. For instance, next notes are appearing as yellow highlights of strings and fingertip positions. Second, fingertip type. This novel form of interaction refers to the act of visualizing the intended type of fingertip on the guitar fretboard, so that it becomes clear which finger should take a note. For instance, each finger is associated with a color. If tip position is highlighted by the finger color, it becomes clear with which finger should take a tip. Third, fingertip movement. This novel form of interaction refers to the act of visualizing the fingertip movement on the guitar fretboard, so that it becomes clear how a vibrato or sliding effect is caused by each finger. For instance, the fingertip movement is visualized by arrows next to the fingertip position on the fretboard. Fourth, attractive note. This novel form of interaction refers to the act of visualizing attractive notes on the guitar fretboard that are legitimate in regard with a certain scale. For instance, aside the precise fingertip position on the fretboard, this includes the corresponding string attack so that a note is characterized. For instance, the next note is highlighted in yellow. Fifth, tip correctness. This novel form of interaction refers to the act of visualizing correct fingertips on the guitar fretboard. Here, for instance, green plus symbols appearing next to the correct finger tapping could visualize a positive feedback. Sixth, tip incorrectness. This novel form of interaction refers to the act of visualizing false fingertips on the guitar fretboard. Here, for instance, red minus symbols appearing next to the incorrect finger tapping could visualize a negative feedback. Seventh, attack correctness. This novel form of interaction refers to the act of visualizing correct string attacks below the corresponding guitar strings. Here, for instance, green string surroundings appearing next to the correct string attack could visualize a positive feedback. Eighth, attack incorrectness. Visualizing false string attacks below the corresponding guitar strings. Here, for instance, red string surroundings appearing next to the incorrect string attack could visualize a negative feedback. Ninth, sound configuration. This novel form of interaction refers to the act of modification of a sound configuration that changes the digital sound design. Here, for instance, shattering an effect device could visualize the switching on or off of a device. 10th, audio signal. This novel form of interaction refers to the audio-based interactions that are realized because of acoustic signals. These can be inserted via microphone and made audible via speakers thereafter. For instance, here a teacher's remote feedback is inserted via microphone, sent through the internet and made audible via the amp connected to the local SensGuitar. As an interim conclusion, I want to picture out that the novel forms of interactions designed can be used to optimize knowledge transfers. In addition to traditional way of making music, these might change the way of learning to play the guitar, making music in bands, making some recordings with producers, etc. In the last session, we have clarified the traditional process of guitar usage. Let's now come to a modification of a process that considers the capabilities of sense instruments. This novel process design refers to an individual research artifact. For this, at this slide, we can find a generalization of a process which shows how sense guitars are used in typical knowledge transfer situations we have clarified in the last presentation session. As the process is abstracted, it shall represent the guitar usage at the same three scenarios. Let's start with a general description of the new process and make it concrete by the context of the education scenario thereafter. On the top of the process, we can identify the same elements of the process we already know. Do you remember the requirement to enhance guitar usage? This is one of the most relevant requirements. Hence, the basic process remains the same. One first difference here refers to the splitting up of the practicing session into session parts. Since the first cycle is created, the traditional guitar usage is not affected at all. Here you can see the practicing session parts, and here you can see the first cycle. It's realized as long as any session shall last. Below the traditional process pictured out here, three further kinds of tasks are realized in parallel. First, a process step called manual feedback. Here, the guitarist is enabled by the SensGuitar and novel forms of interactions to manually feedback the current guitar playing. Please remark, the SensGuitar is considered as IT system in this case. Second, a process step called automated feedback. Here, the guitarist is enabled by the SensGuitar because the SensGuitar generates a feedback autonomously. Please remark the SensGuitar is considered as cyber-physical system in this case. Third, a process step called remote feedback. Here, the guitarist is enabled by the SensGuitar, which is used as interaction partner with remote instances. It takes all kinds of sensors, actuators, processors and communicators into account, too. Thus, it functions as cyber-physical system, in this case, too. Let's now come to an example of the context of the education scenario. As usual, the musician gets guitar lessons once a week. Here, the teacher and the musician cooperate on site. Typically, the teacher presents exercises at a first collaborative session. In individual practicing sessions, the musician then does homework on the exercises discussed with the teacher. Please remark, if the musician does something wrong, incorrect patterns are reinforced traditionally. Because of the new sense instrument process design, the musician is supported as follows. First, a process step called manual feedback. Here, the guitarist is enabled by the SensGuitar and novel forms of interactions to manually feedback the current guitar playing. For instance, attractive fingertip positions are visualized so that the guitarist can feedback its own actions. Since the SensGuitar is considered as IT systems in this case, hopefully the practicing session part is more valuable for the musician. Second, a process that's called automated feedback. Here, the guitarist is enabled by the SensGuitar because the SensGuitar generates a feedback autonomously. For instance, the guitar corrects incorrect fingertips, late timing attacks, etc. Since the SensGuitar is considered a cyber-physical system in this case, hopefully the practicing session part is more valuable for the musician. Third, a process step called remote feedback. Here, the guitarist is enabled by the SensGuitar, which is used as an interaction partner with remote instances. For instance, a human teacher is connected remotely and provides ad hoc feedback to the current playing. Since the SensGuitar is considered a cyber-physical system in this case, hopefully the practicing session part is more valuable for the musician. Hopefully the experiments will prove knowledge transfer optimization and positive effects on the musician's guitar playing. Having a next session with the teacher. The exercise is faced in a collaborative session. Here, a feedback is generated by the teacher for improving the musician's guitar playing. Hopefully, this intervention is from a high quality because inefficient patterns have not been reinforced during the previous week. This cycle is repeated as many weeks as the desired output has been realized. Okay, having faced the education scenario and its knowledge transfer situations, one can recognize the following. The musician is supported by the design because the SensGuitar is considered as an active IT system and as a cyber-physical system in addition. Let's focus on the second common scenario. The musician gets paid sessions at a recording studio. Here, the producer and the musician cooperate on site. As usual, the producer does recordings in the first session. If this is not satisfying, the need for optimization is discussed. In individual practicing sessions, the musician then does homework on the optimization discussed with the producer. Please remark, if the musician carries out a change which does not improve inefficiencies, incorrect patterns are reinforced traditionally. Because of the sense instrument process design, the musician is supported as follows. First, a process step called manual feedback. Here, the guitarist is enabled by the SensGuitar in novel forms of interactions to manually feedback the current guitar playing. For instance, attractive effect chain combinations are visualized so that the guitarist can feedback its own selections. Since the SensGuitar is considered as IT system in this case, hopefully the practicing session part is more valuable for the musician. Second, a process step called automated feedback. Here, the guitarist is enabled by the SensGuitar because the SensGuitar generates a feedback autonomously. For instance, the guitar corrects incorrect effect chain configuration. Since the SensGuitar is considered as a cyber-physical system in this case, hopefully the practicing session part is more valuable for the musician. Third, a process step called remote feedback. Here, the guitarist is enabled by the SensGuitar, which is used as interaction partner with remote instances. For instance, a human producer is connected remotely and provides ad hoc feedback to the current effect chain combination. Since the SensGuitar is considered as a cyber-physical system in this case, hopefully the practicing session part is more valuable for the musician. As we have spoken about session parts, these three kinds of new tasks can be realized in parallel and in addition. Hopefully, experiments will prove the knowledge transfer optimization and positive effects on the musician's guitar sound configuration. Having a next expensive session with the producer. The recording is repeated in a collaborative session. Here, again, a feedback is generated by the producer for improving the musician's guitar playing. Hopefully, this feedback is from a higher quality and refers to smaller intervention in order to correct inefficient patterns, because these have not been reinforced during the previous practicing session. Further, the expensive recording time can be reduced. The cycle is repeated as many sessions as the desired output has been recorded. Okay, having faced the production scenario and its knowledge transfer situations, one can recognize the following. The musician is supported by design because of the SensGuitar is considered as an active IT system and cyber-physical system in addition. Let's focus on the third common scenario. The musician gets band lessons once a week. Here, the band members and musician cooperate on site. As usual, the band carries out a first jamming session. If this is not satisfying, the need for optimization is discussed. In individual practicing sessions, the guitarist then does homework on the optimization discussed with the band. Please remark, if the musician carries out a change which does not improve inefficiencies, incorrect patterns are reinforced as traditionally. Because of the new sense instrument process design, the musician is supported as follows. First, process step called manual feedback. Here, the guitarist is enabled by the SensGuitar and novel forms of interactions to manually feedback the current guitar playing. For instance, track the fingertip positions, which are in the context of the band's current playing, are visualized so that the guitarist can feedback its own actions. Since the SensGuitar is considered as an IT system in this case, hopefully the practicing session part is more valuable for the musician. Second, a process step called automated feedback. Here, the guitarist is enabled by the SensGuitar because the SensGuitar generates a feedback autonomously. For instance, the SensGuitar corrects incorrect fingertips, late timing attacks, etc., which is in the context of the band's current playing. Since the SensGuitar is considered a cyber-physical system in this case, hopefully the practicing session part is more valuable for the musician. Third, a process step called remote feedback. Here, the guitarist is enabled by the SensGuitar, which is used as interaction partner with remote instances. For instance, a band member is connected remotely and provides feedback ad hoc to the current playing. Since the SensGuitar is considered a cyber-physical system in this case, hopefully the practicing session part is more valuable for the musician. As we have spoken about session parts, these three kinds of new tasks can be realized in parallel and in addition. So the traditional process is not affected, it's enhanced. Hopefully, experiments will prove the knowledge transfer optimization and positive effects on the musician's band jamming sessions. Having a next session with the band, here, the song is repeated in a collaborative session. Here again, a feedback is generated by the band for improving the musician's guitar playing. Hopefully this feedback is from a high quality and refers to a smaller intervention in order to correct inefficient patterns because these have not been reinforced during the previous practicing session. Further, the spare joint band time can be reduced. This cycle is repeated as many sessions as the desired output has been realized and the band is happy. Okay, having faced the band scenario and its knowledge transfer situations, one can recognize the following. The musician is supported by design because of the SensGuitar is considered as active IT system and cyber-physical system in addition. Let's come to an interim conclusion. Having faced three kinds of traditional knowledge transfer situations in guitar context, one can recognize the following. Traditionally, the guitar is considered as passive, tangible resource object only. Because of the process design, the novel process design, the musician is supported by the SensGuitar because it is considered as active IT system and cyber-physical system in addition to its tangible resource function. At least this accounts for the three scenarios addressed and the standard electric guitar considered. Let's conclude the design of the SensGuitar. As a summary, with this session we have focused on the design for constructing the SensGuitar. We have clarified novel sensitive instrument design which shall enhance the SensGuitar. We have clarified the architectural embedding of sensitive instruments enabling the SensGuitar. We have focused on novel forms of interactions that need to be considered by the SensGuitar in order to generate feedback. We have clarified the concept of knowledge transfers, how to improve guitar learning with the aid of the SensGuitar. Finally, we have focused on the abstracted novel process designs to generalize scenarios and associate knowledge transfers. These are designed to realize knowledge transfer improvement by design. So, we are best prepared for building on this and we can focus on the demonstration next. Okay, so much about the new topic for today. Since I assume you are happy to have a break before we deepen thematically here, we will end today's session. So you have a chance to think about stuff you have seen and you are fresh for more challenging topics in the next session. Details on the next session you can see at this slide. Hopefully we meet there again. So much from my side today. I thank you for your attention and I'm glad about every email and every exchange about the SensGuitar, be it research projects, becoming part of the open source development team or consulting projects in the economy. Just ask or write an email. Those who would like to learn more about the concept of sensitive instruments, such as the SensGuitar, I invite to have a look on the websites, to visit the public repository where you will find the hyperlinks to the respective references, tutorials, courses and written work. Also, further examples can be found here so that an artifact zoo can be built, simplifying your start with the SensGuitar, for instance. Okay, let's see if there are some questions at the chat. So far I can't recognize any questions, so if you have any questions coming after the session or being offline, just feel free or be invited to collect your questions and to take them to the next session. I would be happy to start a dialogue and communicate about this kind of ideas I have issued, and so that the feedback can be taken in order to include this kind of feedback in the development process and to consider to create a next prototype which is even greater than before. So far so good. Thank you for your attention and I'm happy to see you soon. Bye.